All right, we are shifting to section 2.7. We will be testing next Thursday, just a heads up. All right, so today and then on Monday we will finish up section 7 and start reviewing for that test. So our objectives today, we're going to verify inverse functions, take a look at what it means to be an inverse function. We're going to actually figure out what the inverse function would be. And then we're going to use something called the horizontal line test to tell if something would have an inverse that's a function. We've talked about a vertical line test in the past. All right, now we have a horizontal one. And then we're going to look at some of the graphing of one-to-one functions and figure out, again, calculate those inverse functions. All right, so we're going to start looking at inverse functions in terms of what their graphs look like. So I'm going to have you actually plot some points for these two functions. Our first one that we're going to graph, f of x equals x cubed plus 1. So we have a little table here we're going to fill in. What happens if we put a 0 in for x? What do we get? 1. Yep. If we put a 1 in, 1 cubed is still 1, plus the other 1 gets us a 2. What if we put a negative 1 in? What happens when we cube a negative 1? It's negative 1 plus the 1 would give us 0. Okay, if we put a 2 in and cube it, we have 8 plus 1 would be 9. If we put a negative 2 in and cube that, we're at negative 8. Adding 1 puts us at negative 7. And if we put a 3 in and cube it, what's 3 cubed? 27. Adding 1, we'd get 28. Okay, so let's go ahead and plot those points. We have 0, 1, 1, 2, negative 1, 0, 2, 9, and negative 2, negative 7. We won't graph the 328. That's off our graph. All right, so does it resemble that cubic twist that we've had in the past? Yes? What kind of transformation did we do to just a plain x cubed graph? Look at your equation. What did we do? We just shifted it up 1. Yes? So that's our basic cubic graph, just moved up 1. Okay. Using different symbols, maybe use x as a different color, something like that. We're going to graph this next one. Okay. This time we've got g of x being the cube root of x minus 1. So if I put a 1 in here, 1 minus 1 is 0. Cube root of 0 is 0. Okay. If I put a 2 in, 2 minus 1 is 1. The cube root of 1 is 1. If I put a 0 in, what do I get for the cube root of negative 1? I still have negative 1. What if I put a 9 in? 9 minus 1 would be 8. What's the cube root of 8? Okay. Can you see why I've selected these specific values to plug in? Makes it easy to cube root them. All right, if we put a negative 7 in, subtracting 1 gives us a negative 8. The cube root of negative 8 is negative 2. Okay, let's go ahead and plot those points. So 1, 0, 2, 1, 0, negative 1, 9, 2, and negative 7, negative 2. All right, that is a very typical cube root graph. Which way has it been shifted? 1 to the right, based on that transformation format we've talked about. So this one we shifted right 1 from a basic cube root. This one we shifted up 1 from a basic cube graph. Okay, what do you notice about those two? Yeah, we just simply flipped the x and y values. All right, compare those and those, right? We've just reversed x and y. Does that follow through the whole t-chart? Is that true? Yes. So what would be my last entry in this table here? 28 and 3. Okay? And you could check it. If you plug 28 in, subtract 1, we're at 27. The cube root of 27 is 3. All right? So these are considered inverse functions. If we put a line, a diagonal line, right through the origin, all right, this is the line y equals x. Those are reflections over that line. In other words, if I folded my graph diagonally on that line, my two pictures would match up. Okay? That is the case with inverse functions. So inverse functions are simply reflections of each other over the line y equals x. So we said that our x and y's just get flipped. So inverse functions are two functions that have a domain of the first function matching the range of the second function. And the range of the first function is the same as the domain of the second. All right, that's just a formal way of saying our x and y's just flip-flop. Okay, what we had for x's for the first one would end up being our y values for the inverse function. Questions so far? All right, so how do we actually go about finding an inverse function? If you're given the original one and they say figure out the inverse function, your first step is going to be to change your f of x into a y. Just think of that as your y value, right? Those are interchangeable. F of x is just telling us that we're starting with a function. Then we're going to rewrite our expression by switching the x's and y's. Wherever you saw an x, you're going to write a y. Wherever you saw a y, you're going to write an x. Okay, so we switch our x and y's. Then we're going to solve for that new y. So we're going to rearrange our equation so that new y is all by itself. And if the inverse is also a function, we can put it back into that function notation using that f with a little -1 exponent. A little hard to see on that. It would look like that. So we started out with a function of x. All right. This is indicating that we have the inverse function of x. I can start out with something that's a function and its inverse is not a function. I can still calculate the inverse. I can come up with an equation for it, but it's not going to pass my vertical line test. It's not going to be a function. Okay? So we only do this last step here if it is in fact a function. Okay? Otherwise, we would just leave it as a y. All right, let's do a few examples. So we said f of x is really a y. Our next step is to flip our x and y's around. So I'm going to rewrite this as x equals 5y minus 7. And now I need to solve for that y. What would I have to do? Add the 7, okay? Then what? Okay. All right. Now what we have to decide is, will that be a function? If I take x plus 7 and divide by 5. Could I also write that like this? Is that equivalent? Yes? And if I say y equals 1/5 x plus 7/5, that's just a line, right? The 1/5 is my slope, the 7/5 is my y-intercept. It's fitting that y equals mx plus b format. Okay? So would a diagonal line be a function? All right, so then we can put that function notation. So we're going to say the inverse of function f is 1/5 x plus 7/5. So if you can at all visualize the shape of that, what that equation would look like if you graphed it, it will help you decide if it's a function or not. All right, next example. Again, f of x is really our y value. We're going to switch our x and y's around. All right, and then what do we want to do? Okay, we're trying to get y by itself, so let's subtract our 2. And then what? Divide by 8. Yeah, now we have to take the cube root. If we were taking an even root, I would have to put the little plus minus sign in front. But when we take an odd root, we don't need that. We've got x minus 2 divided by 8 being cube rooted. We could actually simplify that just a little bit more because we know the cube root of 8 is 2. So I could just have the cube root on the top part and have just a plain 2 on the bottom. Okay, that would be a little more simplified. Is that a function? We graphed a cube root at the beginning of notes today, right? We had that kind of sideways twist. Okay, would that pass the vertical line test? Yes. So we can say f inverse of x equals that. Okay. For our next one, we do have a little extra work on this one because you'll notice that there are 2 places where there's an x. So when we switch our x and y's, we're now going to have 2 places where there's a y. And in order to solve for y, we have to somehow get those all to be together. Okay, so this will take a couple extra steps here. First thing I'm going to do is multiply that chunk, that y minus 1 piece. I'm going to multiply it to the other side. Okay, so I don't have a fraction to deal with. So I have x times this y minus 1 equals 2y plus 3. Then I'm going to distribute that x. So I have xy minus x equals 2y plus 3. Okay, now the trick to solving this is any term that has a y in it, you want to put on the same side. Any term that doesn't have a y, you want to put on the opposite side. So I'm going to move this 2y piece over here, and I'm going to move this plain x over there. Okay? So every term that has a y has to be on the same side. So I'll have xy minus the 2y, if I bring it to the left. Then I'm going to add the x to the other side, and I already have a 3 over there. Okay, that's the key step, because now I can factor out a y on the left side, and now instead of having 2 places where there's a y, it's all 1. Okay. And my last step then would be to divide the x minus 2 chunk back over to the other side. All right. Take a couple minutes, think about those steps that we just did. That one was a little more involved than some of the ones we've done previously. Would that be a function? Grab your calculators. I want you to type this in your calculator, but you're going to need to put parentheses here and here. Go ahead and graph it and see what shape you get. All right, so quick sketch of your graph looked like what? Yes? So would this pass a vertical line test? And on some of your calculators, you might have seen a vertical line drawn in here. That's not actually part of the graph. What's happening is your calculator is drawing this part in, and then it's trying to jump up to the top to continue that, and it kind of drags the pencil. So that vertical line is not part of the graph. All right, the newer calculators don't show it, but some of the older ones do. So would it pass the vertical line test? Yes, which means it is a function. So we could write it as the inverse of f equaling x plus 3 divided by x minus 2. Okay? Questions on actually calculating the inverse of something? All right. Does every function have an inverse that is a function? I actually answered this question earlier in the notes. What did we say? No. For a function to have an inverse that's also a function, it has to be what's called 1-to-1. And what that means is for every x, there's exactly one y, and for every y, there has to be exactly one x. All right? Every x has to give you a single y. Every y has to be paired with a single x. No duplicates. So our question, will y equals x squared have an inverse that is a function? It has an inverse. The question is, will it be a function? So my first question for you is, what does y equals x squared look like? That's a parabola, right? Our basic parabola. All right, so if we were to graph that, 0, 0, 1, 1, 2, 4, 3, 9, and then its opposite side. So we are agreeing that this is a function. Now the question is, will its inverse be a function? So think about your t-chart. We said for y equals x squared, we could do -2, we get a 4. -1 was 1, 0, 0, 1, 1, 2, 4. When we graph the inverse, what do we do with those x and y's? We reverse them, right? So if I were to plot the inverse function, instead of -2, 4, I would have to graph 4, -2. Okay, let's plot that point. 4, -2. My next point would be 1, -1. 0, 0 is still going to be the same. Instead of 1, 1, that one's going to stay the same too. Instead of 2, 4, we would have 4, 2. So my inverse is really a sideways parabola. Does that pass our vertical line test, the green one? No. Now, that is one way of telling if something's a function and if its inverse will be a function, looking at the graph. We also can look at it algebraically. So if I were to say, just find the inverse function of this, we switch our x and y, and then we solve for y. Well, how do I solve for y if it's being squared? We square root it. And remember, anytime you take a square root, you have to include that plus minus. Right there, that should be a big red flag. For every x that I plug in there, I'm getting a positive and a negative answer out. For it to be a function, that can't happen. Okay? So, that little plus minus is a big red flag. Your inverse isn't a function. Okay? So again, looking at our chart here, if we just compare those two, remember we've switched it. So for my inverse function, the green one, my table would have been 4, -2, and I would have had a 4, 2. So for the same x value of 4, I'm getting a positive and a -2 out. Okay? We can use that horizontal line test to figure this out. So I asked you before, what does a y equals x squared graph look like? And you said a parabola. That parabola does pass a vertical line test. So the parabola itself, y equals x squared, is a function. Would it pass a horizontal line test? In other words, if I draw any horizontal line through that parabola, is it going to hit my graph in just one spot? No, it's hitting it in two spots. So because it fails that horizontal line test, that tells me that when I find the inverse would fail a vertical line test. Does that make sense? So you can decipher whether the inverse will be a function without actually knowing what the graph of the inverse looks like. You can base it on the original graph. Okay? All right, the last topic today is to actually algebraically prove that two functions are inverses of each other. Graphically, we could look at tables, we could look at our ordered pairs, and do they just reverse our x and y's? But this is asking you to algebraically predict it. Okay? To do that, you have to do two compositions. You have to do f of g, and you have to do g of f, so both directions. And when you do the compositions, your answer should come out to be just an x for both of them. Because if something is an inverse, it should be undoing all of the steps that the original function did. So when you compose them, they should undo each other and just give you an x at the end. Okay? So we're going to prove that. Function f, which is a 4x minus 7, and function g, x plus 7 divided by 4, that they are inverses of each other. Okay? So I'm going to start out f of g, which means I start with function f, 4 times something minus 7, and I'm going to substitute in function g. Okay? The order that these things undo each other is important. On your test, you will have to show me this step, and then you're going to have to show me each step. What is the thing that is getting undone in each step? So what's the first thing that would cancel in this one? The 4's. All right? We have this x plus 7 that's being divided by 4, and then we're turning around and timesing it by 4. So the first thing that cancels here is that the timesing and dividing by 4 undo each other. So that leaves me just an x plus 7 minus a 7. Now the 7's undo each other. I'm adding 7, I'm subtracting 7, and I'm going to end up with plain x. Okay? When I do the reverse direction, now I'm going to be doing g of f. I'm going to start with g function, something plus 7 divided by 4. And what am I dumping in? Okay? Now looking at this one, what is going to happen first? What's going to be undone? We've got 4x minus 7 plus 7 divided by 4. The 7's get reduced first. Because before we divide by 4, we have to clean all that up on top. Okay? So this is going to turn into 4x divided by 4. The minus 7 plus 7 cancel each other out. Then I can divide and I end up with an x. So notice that the order the things canceled each other out was just reversed. In the first one, the 4's dropped out first, and then the 7's. On this one, the 7's dropped out first, and then the 4's. Okay? You have to show me that you know the order things are canceling. Here's what I often get on a test. Students do this. They go, that's not worth any points. You haven't shown me how that thing is being undone. I agree that all of those things eventually go away, but the order they go away in is different depending on whether you're doing f of g or g of f. So make sure you're showing me all of these steps like in this example. Okay? We don't want to do this. Any questions? All right. Your assignment, page 309 to 310, numbers 1 to 37 odd. Obviously, I want to see the work you're doing to get to your answers.